In this video, we're going to look at conditional probability and independence. So we're going to start off with an example. It says approximately 15% of adult men in the U.S. are more than 6 feet tall. Therefore, if a man is selected at random, the probability that he is more than 6 feet tall is 0.15. Now assume that you learn that the selected man is a professional basketball player. With this information, the probability that the man is more than 6 feet tall becomes much greater than 0.15. This is an example of a conditional probability. We've done conditional probabilities before. We just called them conditional distributions, and we were using percents at the time. But you have done conditional probabilities before. We denote a conditional probability with a line between it. So this is the probability of B given A. By definition, the formula is that the probability of B given A is going to equal the probability of A and B, the intersection between the two, divided by the probability of A. So let's look at a contingency table, because this is where you started off with what you did in Chapter 3. So we're going to just kind of use what you've learned before from Chapter 3 to look at some of the old things that we've learned so far in a couple of the videos and the conditional probability. So we have a table here. It says a study is undertaken at a certain college to determine what relationship, if any, exists between mathematics ability and interest in mathematics. The ability and interest for 150 students was determined, and the results are in the following table. If one of the participants in the study is randomly chosen, find the following probabilities. So it says, what is the probability that a person has high interest in mathematics and grade level ability? So we're looking at the intersection between the high interest and the grade level ability. And so the students that have both of those are these 19 students right here, out of the total 150 students. So the probability that they have a high interest in mathematics and grade level ability is going to be 19 out of 150. And this totals as a decimal is 0.1267. The next part says, what's the probability that the person has high interest or has grade level ability? For a contingency table, the events are never going to be mutually exclusive. There's an overlap. We just found it. These 19 students are in both categories. They're both high interest in mathematics and grade level ability. So we need to use the formula. This is going to be the probability that they have a high interest in math plus the probability that they are at grade level minus the intersection between the two, high interest and grade level. So the probability that they have a high interest, well, we have a total of 55 students out of the 150 that have high interest. So this will be 55 out of 150. The probability that the student is at grade level, there's a total of 51 students at grade level, so 51 out of 150. But these 19 students were counted twice in both of these totals. So we have to subtract them off so that they're only counted once. And this will give a total of 87 out of 150, which is 0.58. The last question says, what is the probability that the person has a high interest rate given that the person has grade level ability? Well, if I'm finding the probability that they have a high interest rate, high interest in mathematics, given grade level ability, then using the formula, this is the probability that they have a high interest in mathematics and grade level ability divided by the probability that they have grade level ability. You're always dividing by the probability of the second one, the given part. Well, we figured out the numerator. That's in this first piece here. The probability of high interest and grade level is 19 out of 150. The probability that they're grade level, we also found that. That's this 51 out of 150. When you multiply by the reciprocal, these 150s are going to cancel off, and you'll get 19 out of 51. I'm showing you using the formula, but honestly, I wouldn't use the formula for this problem. I would use the same method we used in Chapter 3, which was if I know that we're given that the person is grade level ability, then I know that I'm only looking at the grade level ability row. Right? I've reduced the table down to just this row. I know that the student is one of those students, meaning that the new total is the 51 students that are grade level ability. And out of those 51 students that are grade level ability, 19 of them have a high interest in mathematics, giving me 19 out of 51. And as a decimal, this is 0.3725. Again, notice I'm not trying to reduce any of the fractions. The fractions are coming straight out of the table. I'm using the fractions to show my work, and then I'm writing the final answer as a decimal. Okay, let's do a given problem or conditional probability problem with a Venn diagram. So we did this one before, and I have the numbers filled out here. It says approximately 42.5% of households have a dog, 28.6% have a cat, and 7.2% have both. And then we calculated the probability that a household would have only a dog, and the probability that a household would have only a cat, and the probability that a household will have neither a dog or a cat. So in this first one, it says, what is the probability that a randomly selected household will have a dog given they have a cat for a pet? So we want to find the probability that they have a dog given that they have a cat. In this case, I would use the formula. This is the probability of a dog and cat divided by the probability that they have a cat. Well, the probability that they have a dog and a cat is 0.072, the intersection between the two. And the probability that they have a cat is the entire cat circle. Don't look at the only cat. It's the whole cat circle. So it's 0.286. And this would be 0.2517. The next question says, what's the probability that they will have a cat given that they have a dog? So I just switched them around. I did that because I want you to see that using the formula, this is the probability of a cat and a dog divided by the probability of having a dog. So the numerator is the same because the probability of having a cat and a dog is the same as the probability of having a dog and a cat, right? It doesn't matter which one I say first, it's an and. So the numerator is the same, it's the denominator that changes because now it's given that the household has a dog, which means I'm looking at the total for dogs, which is 0.425. And this will give a probability of 0.1694. So a big thing that we use conditional probabilities for is to determine independence. This is another topic that came from Chapter 3, and we discussed it a little bit when we were looking at bar graphs and comparing a marginal distribution with a conditional distribution. Now we're going to use a formula to determine independence. So remember that two events are independent if one does not affect the other. So in this case, if one event does not affect the probability that the other event occurs. So to determine if two events are independent, you figure out the probability of one of the events. It doesn't matter which one, just figure out the probability that one of the events occurs. Then figure out the probability that that same event occurs given that the second event occurs. If those probabilities are the same, then event B had no impact on the probability of event A, and therefore the events are independent. So let's look at this example. It says 56% of students at a college live on campus, 62% of the students have a meal program, and 42% live on campus and have a meal program. Are the events living on campus and having a meal program independent? So I'm given two events. I'm just going to choose one of them to be event A. So let's say we let event A be the living on campus. And then event B would be that they have a meal program. Well, the probability of event A, the probability that they live on campus, that's given to me in the problem. It's 0.56. I want to compare that to the probability of event A given B. So does having a meal program change the probability that a student lives on campus? So this would be the probability of A and B divided by the probability of B. Well, it says that 42% of students live on campus and have a meal program. So the probability of A and B is 0.42. And the probability of B is the probability that the student has a meal program, which is 0.62. And 0.42 divided by 0.62, I have the wrong thing on my paper. So let me do this calculation quick. This is 0.677. So notice that the probability that a student has, or a student is living on campus changed. So since the probability of A does not equal the probability of A given B, that would mean that A and B are not independent. Right. Having a meal program changed the probability that a student lives on campus. Let's look at another one. So again, back to the dog and cat problem. It says, again, 42.5% of households have a dog, 26.8% have a cat, and 7.2% have both. Are the events owning a dog and owning a cat independent? So we're going to choose one of them and then find that same probability given the other one. So instead of using A and B, I'm just going to use the events. So let's look at the probability of observing a household with a dog. Well, that's given to us in the problem at 0.425. We're going to compare that to the probability that a household has a dog given that they have a cat? Does having a cat change the probability of having a dog? Well, this is going to be the probability of having a dog and a cat divided by the probability of having a cat. The probability of having a dog and a cat is 0.072. That's that intersection in the middle. And the probability of having a cat, remember, use the whole cat circle for this one. This is 0.286. And when you divide these, you get 0.2517. So the probability of having a dog is not the same as the probability of having a dog given that they already have a cat, which means that these are not independent. A household that already has a cat is less likely to have a dog. So we're going to go back to that grade level ability and interest in mathematics and talk about independence again. So this says, are ability and interest independent? So I want you to notice that it's not asking if two events are independent, but it's asking if two variables are independent, right? Because each variable has three different events. The ability variable has the low event, average, and high event. And the ability, I think I messed that up. The ability has three events, which is below grade level, and above grade level. And the interest has three events at low, average, and high. So what we want to do is we want to pick any one event from each variable. It doesn't matter which one we pick. So we'd already talked about high and grade levels. So let's just pick those. So let's compare, let's let event A be high interest and event B be grade level ability. So then the probability that a student has high interest, we figured this out. It was 55 over 150. And that is 0.3667. And we want to compare that to the probability of having high interest given grade level ability. Remember that this is the probability of high interest in mathematics and grade level ability divided by the probability of grade level ability. So this was 19 out of 150 divided by 51 out of 150. Or I said, forget that and just look at the grade level row and we get 19 out of 51, which was 0.3725. So the question is, are these the same? Well, if I had only rounded to 2 decimal places, I would have gotten 0.37 for both of these. So it would be really hard for me to say that these two events are not independent. They look independent to me. But the problem is asking if the variables are independent. And if the variables are independent, it means any combination of events will come up as independent. So I found 2 events, one from each variable, that turned out to look like they were independent. Let's see if that happens again. So let's pick 2 different events. Let's let A be low interest And let's keep B at grade level ability. So if we find the probability of low interest, well, I have 60 out of the 150 students that have low interest, and this is 0.4. The probability that a student has low interest given grade level ability, I'm going to forego the formula right now. I'm looking only at grade level ability. And so I know this is out of 51, and out of the 51 students, 15 of them have low interest. And 15 out of 51 is 0.294. Now I've found two probabilities that are definitely different, 0.4 and 0.3. Those are not close enough to say that these two events are independent. So since I found two events within these two variables that are not independent, I would therefore conclude that the variables themselves are not independent. So ability and interest are not independent. Right? If they were, they would have to be independent for every different scenario of events that we chose. And since we found one example of two events that are not independent, it means the variables themselves are not independent.